Our new frontier is in space. Someday, man will travel the moon. In the year 1610, Galileo viewed the moon through man's first telescope. Since then, we have learned many things about the moon. For example, we believe that there is no lunar life, that the moon has no atmosphere and no water. Surface temperatures on the side toward the sun are near boiling. On the dark side, they are far below zero, colder than any place on Earth. We know many other details about the moon, but we need to know much more. This is the story of one phase of the search for knowledge, the flight of moon rocket Pioneer 4. We are in the communication center of the Jet Propulsion Laboratory located in Pasadena, California. Teletype and radio links are maintained with principal space probe tracking sites, and of course with the Atlantic Missile Range in Florida. Nearby is the big computer which is used to determine flight trajectories and to evaluate the success of space probes. 3,000 miles away across the continent at Cape Canaveral, an Army Juno II rocket is poised for the launching of Pioneer 4. During the last 2 days, 2 attempts have been made to launch this moon rocket. Until now, there have been both weather and technical difficulties. We are now in the 3rd countdown. If there are no holes, the command will soon be given to clear the launching area. Liftoff will be in 35 minutes. Located only 100 yards from the launching pad is the blockhouse. Here, scientists are performing the last-minute checks and operations, which we hope this time will result in placing the free world's first successful lunar vehicle in its planned trajectory. More than a week ago, the big first-stage rocket, the Army's Jupiter Intermediate Range Ballistic Missile, was brought to the launching pad. The huge missile was erected and placed on its launcher, and the gantry with its adjustable working platforms was moved into place. Engineers and technicians began checking out the rocket's thousands of components and assemblies, all of which will have to function perfectly if the flight is to be successful. 5 days ago, the solid propellant high-speed stages were removed from the hangar. Rocket stages 2 and 3 are contained in a tub which fits inside the shroud of the Jupiter. Stage 2 is a cluster of 11 solid propellant motors arranged in a hollow ring. Stage 3 consists of 3 solid propellant motors, also contained in the tub, inside Stage 2. When the high-speed stages arrived at the launching pad, they were hoisted into the gantry and placed on the Jupiter. Although mechanically similar to the hardware used to launch the Army Explorer satellites, these high-speed stages utilize higher performance propellants in order to obtain a greater thrust. The Jupiter has a diameter of 8 feet 9 inches and is 60 feet long. For this moon mission, the Army Ballistic Missile Agency modified the Jupiter. Different guidance equipment was installed. Instead of carrying its usual nose cone, a special aero-dynamic shroud was fashioned to enclose the upper stages and the payload, to protect them against the extreme heating which will be encountered as the vehicle rises through the Earth's atmosphere. The first launching attempt was scheduled for 2 days ago, 18 minutes, 16 seconds past 10 p.m. on Saturday, February 28. An overcast sky with visibility restricted to a 1,000-foot ceiling forced postponement of the attempt. Also earlier that day, there was the threat of a hurricane in the area. By the end of the day, the weather was still threatening, but showed some promise of improvement. Yesterday, on Sunday, March 1, a second attempt was scheduled, though the weather was still uncertain. Heavy rains were forecast for late afternoon. Yesterday morning, routine sterilization of the payload was accomplished. Scientists are concerned that Earth bacteria might contaminate the moon's surface if the payload impacts on the moon. Yesterday afternoon, the payload was attached to the fourth and final stage motor and, under a protective covering, taken to the launching pad where the assembly was hoisted into the gantry for mating with the high-speed cluster. The shroud was then lowered over the payload and secured to the vehicle. At X-minus 320 minutes, fueling operations commenced and proceeded normally. But at X-minus 300, a hold was called to permit a check of range safety radar. It first appeared that it would be necessary to cancel the test, but repairs were accomplished within a 30-minute period. The count was recycled and resumed at X-minus 280 minutes, when a final check indicated that weather conditions would definitely permit the firing. The countdown then proceeded normally, and liquid oxygen loading was accomplished. Final payload checks were made at X-minus 31 minutes. And at X-minus 8 minutes, the order was given to switch the payload from external to internal power. The switchover was not successful. A hold was called, and time recycled to X-minus 31 minutes. The vehicle was reoriented on the launcher as an attempt was made to locate the difficulty. At 11:28, time was again started. But 1 minute later, at 11:29, the order was reluctantly given to cancel the test. Working in high-velocity winds and rain, engineers removed the aerodynamic shroud to make the payload accessible. After a preliminary inspection of the payload, it was removed to the laboratory where faulty components were discovered. Consequently, this payload was rejected in favor of a spare. This morning, Monday, March 2, the weather was clear and cool, perfect for a missile launching. The test was scheduled for 10 minutes, 50 seconds past midnight. Because of the new firing time, the probe will enter space at a different angle to the sun. It therefore was necessary to repaint the payload, changing the white temperature control pattern to black. At 4:30 this afternoon, the payload was brought out, and this time taken up the gantry elevator. At the same time, pre-checking on the Jupiter was completed, and at 4:45, the missile was rotated to final azimuth position. At X-minus 60 minutes, there was a worry that data handling equipment on the Doppler was in trouble. This has been cleared up, and now we are coming down to X-minus 31, the crucial time for the third launching attempt. However, in the months that preceded this firing, there were other preparations equally important to the success of the mission. Near Goldstone Dry Lake, just south of Death Valley, California, a huge radio tracking antenna was constructed to provide a means of tracking the probe and receiving the scientific data it transmits. The Goldstone Test Station is a vital link in the Pioneer 4 firing. Also a part of the tracking complex is a smaller antenna located in Puerto Rico. The tracking data received by the two antennas and at the launching site will be immediately transmitted to the JPL Computing Center in Pasadena for reduction and analysis. Transmission of such information can be accomplished in a matter of minutes. In addition to teletype communications, radio contact with Cape Canaveral is maintained.
This is Cape Canaveral. We are continuing with the countdown. The time is now X-minus 20 minutes. Mark.
Firing time is only 20 minutes away. We have been informed that the payload has been switched to internal power. All equipment is functioning perfectly and the weather remains clear. It is unlikely that there will be any further difficulties. However, any changes in schedule will be immediately relayed to this center. Planning for the Juno II series of lunar space probes, which had been designated Pioneer 3 and Pioneer 4, had reached an advanced stage early in 1958. At that time, Dr. William H. Pickering, director of the Jet Propulsion Laboratory, evaluated the proposed lunar flights from the perspective of past events.
Our plans are now completed, but before I discuss them, it is interesting to depart from the subject for a moment and see how we arrived at this place in time when we calmly talk about the exploration of space. After Sputnik, but even before Explorer 1 was authorized, a special Jet Propulsion Laboratory study outlined plans for a moon probe. This report said, in part, the launching of the first Earth satellite by the USSR has had a tremendous impact on people everywhere. It is imperative that the United States produce a significant technological advance by providing the world with a useful moon rocket. This work is required in preparation for the time when man himself will be engaged in the supreme adventure of exploring the moon, the planets, and eventually even outer space itself. We are now committed to the following. First, we will begin the task...
And so the vehicle design was frozen, and payload missions for the Juno II series were defined. Pioneer 3 would provide a test of the guidance and propulsion systems, obtain radiation data, and check equipment proposed for future flights. The Pioneer 4 payload would then be exactly determined using the data from Pioneer 3. Both flights would attempt to pass beyond the moon and to go into orbit around the sun. In the fall of 1958, the State University of Iowa completed preparation of the radiation package to be flown in Pioneer 3. Dr. J.A. Van Allen, who originated the radiation experiments, summarized the results obtained from the Explorer firings.
Some idea of the nature of these observations can be gathered by looking at this chart. Now, this represents the Earth with its magnetic axis. Each one of these contours or curved lines is a contour of constant radiation intensity, in which the radiation intensity increases as one goes outwards from the Earth. Now, with the moon shot, we expect to shoot right through this whole pattern of radiation and determine how high it goes, at what radius from the Earth it has its maximum, and in what manner it falls off as we go to very great distances from the Earth. Now, it is not at all necessary that our apparatus go near the moon or strike the moon for this purpose. The essential thing is that the moon probe carry the apparatus to very great distances from the Earth.
The first flight test of the Juno II program occurred in December 1958 with the launching of Pioneer 3. Pioneer 3 did not succeed in reaching the vicinity of the moon. However, the probe reached an altitude of 63,500 miles, and valuable radiation information was obtained. After the data from the Van Allen experiment had been analyzed, Dr. Everhart Rexton of JPL disclosed some of the findings.
Using the earlier results from Explorer 4 and later results from Pioneer 3, Dr. Van Allen was able to show the existence of two radiation belts high over the tropic and temperate zones of the Earth. The first zone is 2,000 miles thick and starts 1,400 miles above the surface. The second zone is 4,000 miles thick and starts about 8,000 miles from the surface of the Earth. There are several consequences to Dr. Van Allen's discoveries. Manned space stations at altitudes of less than 500 miles are comparatively safe. The regions of high intensity are somewhat smaller than originally believed, so that if man wished to escape into space, he could either make a dash through these belts or take his ride leaving by way of the poles. But more information is needed before man can safely venture into space. It is now vital and necessary that the extent and the nature of the dangerous radiation be exactly understood and mapped.
Based on the results of Pioneer 3, it was decided that Pioneer 4 would repeat the experiment, seeking additional radiation information.
Moon probe carries instrumentation that performs a variety of missions. It is a tribute to the JPL miniaturization program that the entire payload weighs less than 15 pounds. This is the assembled instrumentation, including the battery, power supply, transmitter, and associated electronics. Here is an assembled payload. During the early portions of the flight, the entire high-speed rocket cluster is spinning in order to maintain directional stability.
We have just been informed that Pioneer 4 liftoff is imminent. Just a moment, stand by. We are attempting to contact the Cape.
Mark, X minus 20 seconds. X minus 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Firing command.
Stage 2 ignition. There goes 3. Stage 4 ignition.
This is Cape Canaveral Central Control. Liftoff was normal. All stages ignited.
The probe is already far out over the North Atlantic. Puerto Rico is attempting to acquire the signal.
The signal was acquired in Puerto Rico on schedule, and probe telemetering is now being monitored. The data now being received will be sent to you as soon as possible.
It will be some time before further information is obtained. But a description of what is happening was provided several days ago by Dr. J.E. Froelich, JPL Project Director for the probe, and Dr. K.H. Davis, head of the Army Ballistic Missile Agency's Missile Firing Laboratory.
To understand fully the complexities of our moon probe project, let's consider some of the basic problems with which we must contend. Our target, of course, is here, or more precisely here. Our objective is to just miss the moon, allowing the probe to pass into the space beyond. The distance to be traveled is difficult even to imagine, nearly 250,000 miles. If you are traveling at the speed of sound, it would take nearly half a month to traverse the distance. Consider now our firing platform, the Earth. If it were standing still, the problem would in many ways be simpler. But it is, of course, revolving on its axis, producing at Cape Canaveral a rotational speed in excess of 900 miles an hour. Our target itself is also moving, orbiting the Earth at an average speed of 2,200 miles an hour. Thus, in order to reach our target, we have to aim about 75,000 miles ahead of where the moon is at the time of firing. That you may better appreciate the complexities involved, Dr. Davis will review for us the flight mechanics of a typical moon firing. Kurt, take over.
Thank you, Jack. You gentlemen are very fortunate. You are going to see the completely successful firing of a probe to the vicinity of the moon. This I guarantee. Of course, you are going to see it only in drawings on a screen, which is a little easier than in actual space. However, if the real probe does succeed, the mechanics by which the success will be achieved will be those which you are going to witness. Cape Canaveral is about 28 degrees north of the equator. Firing will be in a generally easterly direction. Exact angle of firing will depend on day, hour, and minute of firing. Following a countdown of many hours, involving a final check of every possible detail, the rocket will blast off. After the burnout of the first stage, the booster motor separates from the guidance compartment and nose section. A brief period of coasting follows. The nose section is then detached by an explosive charge and moved out of the way by a small rocket motor. Meanwhile, jets of the guidance system have been activated to place the high-speed stages and the payload in proper firing attitude or direction. Now, with the rocket in effect aimed at its target, the spin-stabilized high-speed stages commence their firing sequence. With the firing of the last stage rocket, the probe has now achieved escape velocity. After a long period of coasting, about 10 hours, the burned-out fourth stage is separated from the probe payload, and the de-spinning device, consisting of weights attached to wires, is activated to stop the spinning motion of the probe. This is to permit a check on the performance of the optical instruments which it carries. The probe payload will now coast on into space to and beyond the vicinity of the moon. Now you know, gentlemen, how very easy, yet how very complex it all really is.
Thank you, Dr. Davis. What you have seen is a presentation of what will happen if every device in our rocket vehicle functions correctly at precisely the right moment. Our final set of problems have to do with tracking the flight of the payload. At takeoff, the probe will be tracked by conventional radar equipment in Florida. A short time later, the downrange station in Puerto Rico will pick up the signal. As the rocket rises on its trajectory, other stations ringing the Atlantic will also pick up its signal. These stations, however, will soon lose contact because of the rotation of the Earth and the greatly increasing distance. At about X plus 5 hours, when the probe is 60,000 miles out, it will come in line with JPL's long-range receiving station at Goldstone, California. This we call the first acquisition. So sensitive is the Goldstone antenna that it will permit measurements of the probe's trajectory, which will be accurate to 1/10 of a degree. At about X plus 17, Goldstone will lose contact because of the rotation of the Earth. However, enough information will have been transmitted to JPL's computer center to predict exact position of the probe in time and space until the second acquisition occurs. This will be at X plus 29 hours, as the probe again comes above the horizon of the Goldstone station. The antenna will then hold contact as the probe passes into the space beyond the moon. This then is the situation before us. The problems we face are almost staggering in their complexities, but we must continue to move ahead.
Almost 1 hour has now elapsed since the firing of Pioneer 4. The first estimate based on the computer predictions will soon be made. I have been told that the payload withstood the acceleration of missile liftoff. We have also heard that the instruments are operating as planned. The trajectory appears to be down 4 degrees and south 2 degrees. This slight deviation, however, will not adversely affect the test objectives. Data from the Puerto Rico tracking station has been coming steadily into the computer center. This data is in the form of punched tape, which is automatically converted to punched cards and fed into the computer. The first prediction has just been released. Stand by. The National Aeronautics and Space Administration is making the first announcement. A favorable flight path has been achieved. it is mathematically certain that Pioneer 4 will reach the vicinity of the moon and will achieve an orbit around the sun. And so the firing of Pioneer 4 became history, a significant step in an orderly procession of events. Bearing out the calculations of the teams of scientists, the men at the Goldstone Test Station made the first California acquisition on March 3 at 3:47 a.m. Pacific Standard Time. On Wednesday, March 4 at 4:33 a.m., the big antenna made contact for the second time. Almost 10 hours later, at 2:26 p.m. Pacific Standard Time, the probe passed within 37,000 miles of the moon. We know now that Pioneer 4 will establish an orbital period around the sun of 392 days. Its closest approach to the sun will be 92 million miles. Its maximum distance from the sun will be 106 million miles. The experiment had been as our scientists had said it would be.
The problems are almost staggering in their complexity, but we must continue to move ahead.
This work is required in preparation for the time when man himself will be engaged in the supreme adventure of exploring the moon, the planets, and eventually even outer space itself.
This achievement places the far corners of the solar system within the reach of man and marks another step in the conquest of time and space. For the future, our task is defined: to enrich knowledge and understanding, and therefore to aid man in fulfilling his peaceful destiny. To this end, we are dedicated.